Okay, so welcome back to the afternoon session. It's a pleasure to introduce Robert Huang, who's currently at Google, and Robert is going to tell us about learning shallow quantum circuits.
Yeah, thank you so much for inviting me here. I'm very happy to give this talk on learning shallow quantum circuits. This is a joint work with Yunxiao Liu, Michael Broughton, Isaac Kim, Anurag Anshu, Zeph Landau, and Jerry McLean. So for those of you who have not heard of the term, shallow quantum circuits are essentially quantum circuits with low circuit depths. For example, here is an illustration of a one-dimensional quantum circuit of depth 3, so a constant depth. But in general, sometimes people refer to shallow quantum circuits to mean constant depths or maybe log depths or sometimes even polylog depths. So due to their low circuit depths, in a way they're quite simple. However, recent works have really shown that they're surprisingly powerful from a computational standpoint. So for now, I'm going to provide a brief review on some of the results that people have known about shallow quantum circuits. So the first example was due to this paper called Quantum Advantage with Shallow Circuits, published at Science in 2018. So in this work, they proved that shallow quantum circuits are unconditionally more powerful than shallow classical circuits. So what does that mean? It basically, in this work, they showed that there's a relational problem. You can think about it as kind of a conditional sampling problem, where the shallow quantum circuits can solve that computational problem very efficiently. On the other hand, they proved that for any shallow classical circuit, it will not be able to solve that problem. Here, for this example, they consider shallow to mean constant depths. So the way they essentially showed that was essentially by showing that in shallow quantum circuits, even though it's shallow, so the entanglement it could generate is very localized. It's a two-dimensional circuit that they consider. Yet, when you perform measurement on the output state, it can generate highly non-local correlation, which cannot be generated in shallow classical circuits. And here they consider shallow classical circuits to mean like classical circuits consisting of AND gates, OR gates, and NOT gates, but all of them acts on a constant number of bits. A follow-up work essentially extends this previous result and enhancing it, and the result was published in Stock 2019 called Exponential Separation Between Shallow Quantum Circuits and Unbounded Fan in Shallow Classical Circuit, where they consider an enhanced family of classical circuits called shallow classical circuits with unbounded fan and AND gates. And in complexity theory, that was often referred to as AC0. So there, instead of having these Boolean gates that acts on a constant number of bits, they consider this addition of a unbounded fan and AND gates. So those are just AND gates that can take arbitrary number of inputs and take an AND over all of them. So these shallow classical circuits with these additional gates are much more powerful than shallow classical circuit. In particular, one can prove that any Boolean function can be represented using a constant depth classical circuits with these unbounded fan and AND gates. However, in general, they have to be exponentially large. And what they essentially show in this work is that shallow quantum circuit can achieve computational task efficiently, whereas any shallow classical circuits with unbounded fan and AND gates would require an exponential size. So while these two examples focuses on comparing shallow quantum circuits with shallow classical circuits or versions of it, one can also compare shallow quantum circuits to an entire family of classical algorithms. So that's a completely different line. One of the first few works is this architectures for quantum simulation showing a quantum speedup, published in PRX 2018. And then there are some gaps in their proof. So in a follow-up work in PRL 2020, they closed these gaps to establish quantum advantages. Essentially, what they showed in this line of work is that shallow quantum circuits can achieve computational problems, basically like sampling problems, that any classical algorithm would require superpolynomial time to achieve, assuming that the polynomial hierarchy does not collapse. So pretty standard assumption for claiming quantum advantage. So the idea here is that when we have these shallow quantum circuits, even though, again, like the entanglement is completely localized, when we perform a measurement on the output state, it can actually generate highly non-local correlation. Kind of similar to like when you have a cluster state, and now you measure all the qubits in the middle. Now you can generate entanglement in the two end. It's very similar to like that, but essentially they can utilize this idea to show that even though shallow quantum circuits only generate localized entanglement, they can be computationally hard to sample from. So, for example, Anthony's talk from yesterday, there's also one of their results showing the quantum advantage in constant temperature Gibbs sampling was also based on reduction to this result, showing that shallow quantum circuits are more powerful than any classical algorithm. So the power of shallow quantum circuit have really raised the hope for the QML community that maybe we can utilize them as some kind of machine learning models that hopefully, in a very optimistic sense, could have some quantum advantage over classical algorithms. And due to this hope, there have been an extensive amount of works, maybe hundreds or thousands of papers, that try to study the problem of learning and training shallow parameterized quantum circuit, which some of them also refer to this as quantum neural networks or shallow quantum neural networks. And not only do they study the problem of learning and training them, there's also a lot of different use cases for utilizing quantum neural networks, which I will briefly review in the following. So what are some use cases that people have come up with? And what's the relevance of training shallow quantum neural network for, say, quantum dynamics and quantum simulation? So the first use case that people come up with is in learning dynamics. So here I want to imagine that in a lab or in nature, there are some unknown quantum dynamics that's happening. And what we would like to do is to learn what that dynamics is and be able to simulate it. So the setting that people often consider is the following. We assume that there's a training set that tells us for certain, say, simple product states, like some input product state, what is the corresponding output state? Or maybe we don't even get the output state, we just get some measurement statistics of the output state. So we collect these training set from the unknown dynamics, unknown quantum dynamics in nature that we wanted to simulate. And then what we do is we try to train a quantum neural network to based on the training set, in the hope that after training, for a new input state that's not in the training set, we can use the quantum neural network to accurately predict the corresponding output state. That's one of the use cases that people have been playing with. There are various algorithms that people tried, and it seems to work in some small scale, medium scale, a few tenth qubits experiment, but it's not entirely clear how well it was scaled. The second use case is related to the first one, but in a sense, there's not really any learning involved. So the second use case is in speeding up dynamics. So here we assume that the dynamics we wanted to simulate is already known to us. It's an n-qubit unitary U, and we are already being given a quantum circuit for it. So maybe this unitary U corresponds to Hamiltonian simulation of some Hamiltonian of interest, and say the quantum circuit corresponds to the trotterization of that Hamiltonian dynamics up to some certain fixed time t. However, oftentimes the Hamiltonian have certain inner structure that may allow one to more efficiently simulate it. So for example, some Hamiltonians are fast forwardable. So if you wanted to simulate for a very long time, there always exists a very short circuit that can do it. But that requires the Hamiltonian to be quite structured. But nonetheless, in general, different Hamiltonians have its own characteristic, and perhaps one can utilize those characteristics to make the simulation much faster. However, in general, it's not clear to us, or it might not be clear how one can implement that efficiently. So one idea that people have proposed, or the QML community has proposed, is to train quantum neural network to find these faster circuit implementation for us. So for example, if there does exist some fast-forwarding circuit that can really implement a long-time dynamics very efficiently, we hope that the quantum neural network will be able to find such a circuit for us. So here, in information theoretically, there's no learning involved because every information is there. We have the unitary. We know exactly what we wanted to implement. But here we want the quantum neural network to learn a faster implementation. So like compile it so that it becomes much easier to run on current devices. That's another use case. The third use case, another use case that people have identified is in generative modeling. It's again very different from the previous two. Here we are given some classical data set consisting of input text and output bit string. So think of it as a standard generative model, like image generation, for example, or other kind of generative modeling for creating distribution, for generating classical distribution. And the goal here is to, or the hope here is to train quantum neural network to be able to generate new output bit strings for a new input text description. One could think of 3 as kind of like the classical version of use case 1. So there have been hopes on this, especially due to all these evidence that shallow quantum circuits can be computationally more powerful than classical algorithms, especially in sampling or relational problem. So there have been hope that maybe one can use it to achieve advantage in generative modeling. So due to all of these use cases that people have found, the community has found, there are also a lot of works that just try to study how well we can train and learn shallow quantum circuits. How well can they scale? And what are the challenges that we run into? For example, the well-known notion of barren plateau. That's one challenge that people might run into. And I will also talk about a few other challenges that people have seen. But basically, as of now, or before our work, the very unfortunate fact is that there is no efficient algorithm known for learning shallow quantum circuits. But people have identified a lot of challenges, which I'll briefly review here. The first challenge is related to optimization landscape. So when the cost function is not global, like there's a local cost function, it's well known that shallow quantum circuit doesn't have barren plateau. But this very nice work, quantum variational algorithms are swamped with trap, provides various theoretical analysis as well as numerical experiments showcasing that even though there's no barren plateau, the optimization landscape of shallow quantum circuits are swamped with exponentially many bad local minima. Essentially, the landscape is very bad, and there are a lot of frustration inside of it, and hence it's very hard to train them. So here is a plot from their paper. It's just a 2D slice of this exponentially large space. But within this 2D slice, we can already see that there's tons of up and downs, and there's tons of local minima inside. And furthermore, one could show that in various cases, these bad local minima, the suboptimal local minima, they're essentially attractors, which means they behave more like traps. That is, if you're kind of close to them, then you get stuck into them. And when you try to escape, like by perturbing it, using noise, etc., you get sucked back to the same point. And oftentimes, because there are too many of them, even if you successfully jump out of one of the traps, you get stuck into another one. So due to this result, the authors found, and also I think many other people have corroborated, that gradient descent and various other local optimization methods, they just get stuck into these traps and fail to efficiently learn. Only when we start out being very, very close to or the true global minimum, then we succeed. But a lot of times it can get stuck due to the bad landscape. So this is a challenge from a more practical perspective when we try to train shallow quantum neural network. Another challenge comes from a more theoretical perspective due to the classical hardness. So in theoretical computer science, there have been tons of work trying to understand and to develop provably efficient algorithms for learning various classical circuits, such as learning shallow classical circuits, called NC0, or shallow classical circuit with unbounded fan and AND gates, AC0, as well as learning decision trees, learning random forests, learning kernel methods, learning support vector machines, etc. A lot of them can all be done very efficiently. However, as we have seen, shallow quantum circuits, they're inherently classically hard to simulate because they can create highly non-local and classically hard distributions. So if one just try to apply these very powerful learning algorithms that are very useful for learning classical circuits to this case, it would just not apply because shallow quantum circuits are not efficiently simulatable classically. So these challenges raises the following existential crisis question. That is, even though shallow quantum circuits has enhanced computational power, are they fundamentally hard to learn? Maybe one could say, maybe that's just the price we have to pay due to their classical hardness. Maybe classical hardness implied they're going to be hard to learn. So a priori, this question, like before our work, this question has been unanswered. But what I wanted to essentially do in the remainder of my talk is to show that the future of quantum neural network is not as bleak as one might have originally thought. And we are going to show that the answer to this question is negative. It's no. They're not fundamentally hard to learn. And in fact, we can write down a very efficient algorithm for learning them. So for the remainder, I would like to present some of the key ideas behind our learning algorithm. And let us revisit this challenge regarding bad optimization landscape. One can ask the following question. Is bad landscape a fundamental feature of a trainable quantum circuit? It seems to be. Like there's barren plateau when the circuit is deep, and when it's shallow, there's these bad optimization landscape, like tons of traps. But and indeed, this is indeed the case. This is a fundamental feature for the standard parameterization of quantum circuit. I mean, that's what this previous paper essentially proved. But basically, the standard parameterization is that we just parameterize all the gates of the quantum circuit. So each gate has some finite dimensional vector associated with it, and there's tons of gates, and then we just try to train them jointly. And it is in that case, there will be a lot of frustration, and the training can easily get stuck in these bad local minima. So, however, while this is a feature of the standard parameterization, we're going to show that there's actually other parameterization of trainable quantum circuits that doesn't lead to bad landscape and can be efficiently navigated. So we call that parameterization by local inversion. And to define this parameterization, let me first define what local inversions are. So suppose we have this n-qubit unitary U. And say V1. We say V1 is the local inversion of this n-qubit unitary U for qubit 1. So here, while I draw U to be a shallow circuit, the notion of local inversion can be defined in general for any unitary U. It doesn't have to be shallow. So what is the local inversion? So basically, if V1 is the local inversion for qubit 1, then it means that when we compose U and V1, so U followed by V1, together, that operation, that transformation, will act as identity on the first qubit and arbitrarily on the rest of the qubit. So that's the definition of local inversion. Hopefully, it's very intuitive. Note that global inversion is something everyone is very familiar with. The global inversion of U is just U dagger. It's just the inverse of U. And for the global inversion of U is unique because U is reversible. But the local inversion may not be unique. For the same qubit, the same unitary, there may be a lot of different local inversion. So there might be a lot of choices for V1, such that when we compose V1 and U, it gets identity on qubit 1. But we don't care about that. That's fine. That's just a property of local inversion. Another important property that we're going to utilize here is that when the unitary U is a shallow quantum circuit, as shown here, it's not hard to see that a local inversion, there always exists a local inversion that only acts on a small number of qubits, like a small unitary, such that it would invert. It would locally invert the first qubit. And to see that, essentially, it's kind of already drawn here. If V1 is selected to be the inverse for the corresponding 4 of these gates, these 4 gates, then after applying it, it will invert all of those gates and reveal the first qubit. And hence, one could see from just that simple graphical proof that for a shallow quantum circuit, there always exists a local inversion that only acts on a small number of qubits. We can similarly define local inversion for the second qubit, V2, and also, of course, for V3, V4, V5, and V6. So here, the illustration just kind of showcases how, for different qubit, the local inversion changes its structure. Essentially, it has to kind of open up like a small ball around that corresponding qubit, like qubit 6, and then try to invert the thing, the entanglement that was created in U. So now, after defining local inversion, one of the most important lemma in this work is the following. Basically, we showed that for any n-qubit unitary U, the local inversions V1 through Vn, so note that there's n local inversions because there's n qubits, we uniquely determine the unitary U. So this lemma holds for any unitary. It doesn't have to be shallow quantum circuit. It could be a very deep quantum circuit, arbitrary unitary. This always holds. So note that a priori, this is not necessarily true. Like for example, if we consider n-qubit state, rho, then the local reduced density matrices, rho 1 through rho n, they will not uniquely determine rho itself. However, one can prove that local inversions actually uniquely determine U. So one can ask, why is that the case? How can we show that? And here I'm going to present a way to kind of also, again, a graphical proof for this lemma. And the way we prove that is by doing the following. Suppose there is some arbitrary n-qubit unitary U. And suppose that V1 through Vn are the local inversions of that unitary U for qubit 1 through qubit n. We don't know what U is, but we do know what these local inversions are. Now, we're going to show that there's actually an efficient procedure that allows us to sew together these n local inversions to create the unitary U. Basically, one can naively or intuitively understood it as like, note that this local inversions, let's say in the shallow quantum circuit case, they only act on few qubits. So some of them act around here and some of them act in different places. And now what we would like to do is to have some procedure that allows us to like bind them together to create this global n-qubit unitary. Initially, each of them would be a small unitary acting on a few qubits. But note that this, the procedure that I'm going to present, they hold in general. So it doesn't have to be shallow quantum circuit U. It can be any unitary U and any local inversions V1 through Vn. Note that they're not unique. But no matter what they are, we can always suit them to create the unitary. So the way we're going to prove that we can create the unitary U using the local inversions, is to show that for any state, psi, for an arbitrary state, n-qubit state psi, we can essentially implement the unitary U onto psi. So note that here we assume that we don't know what U is. We only know what these V1 through Vn are. We try to use them to create an action of U onto any arbitrary state, and hence we create the unitary U. So algorithmically, it looks like the following. First step, we're going to initialize two n qubits. N of the qubits is the one, the initial state, the input state. And then the other n qubits are all initialized in a maximally mixed state. Now we're going to use a very basic property of maximally mixed state, which is when we conjugate it by any unitary, it will remain the maximally mixed state. So here this step we're not doing anything physically. We just kind of imagine in our head that there's the unknown unitary U is now being applied to the maximally mixed state. We can do that because it doesn't really change the maximally mixed state. The maximally mixed state is still maximally mixed. But this imagination is going to be quite useful in the following way. So after we imagine U being there, we now apply V1 onto that maximally mixed states, that n-qubit maximally mixed state. And recall the definition of local inversion. By composing U and V1, it would create an identity on the first qubit while being arbitrary on the rest of the qubits. So now it kind of uncovers this first qubit, which we can just dispose it by, say, tracing it out and throwing it away. So now after we do that, there will be one last qubit in the system. We can think about it just forgetting them in the practical setting. And now we do a rewiring. So this rewiring can be done like using a swap, for example. Just rewire it. So now the first qubit of this psi, initially the psi is just sitting there on its own. There's two n qubits. Now we just rewire it into the place where it's left open. And then we do an inversion. We apply the inverse of the local inversion, here V1 dagger. So if we only look at, so if we forget about the rewiring step, all we're doing is we have U, and then we apply V1, which gives rise to this identity tensor, some arbitrary operation. And now we apply V1 dagger, which kills the V1 that we applied, and hence it will heal back to the n-qubit unitary U. So now from here, we've seen that through these steps, what we have done is we remove one of the maximally mixed state single qubit maximally mixed state, and we kind of rewire the first qubit of psi into U. So these are the 6 steps that allows us to do that. And now if we focus on the second qubit, we can essentially achieve the following action. We remove that qubit, and we allow the second qubit to be plugged into this kind of imagined U. So note that U at the beginning was just in our imagination. But by slowly running these steps, we can turn U, we can kind of materialize U, so it actually become acted onto an arbitrary state psi. So that's the full suing procedure. Note that there's flexibility in how this suing procedure works. Right now, I've talked about it in terms of like 1 qubit at a time. We consider first qubit and second qubit and so on. But actually, in the case of shallow quantum circuit, the more efficient way to do things is we consider a tons of kind of non-overlapping or sufficiently distant qubits and just apply this 6-step procedure kind of in parallel. And that allows us to create, so let's say the unitary U is a shallow quantum circuit. Using this sequential method, the suing technique will sue into a linear depth circuit. But if we use a slightly more clever way, like doing the suing technique in parallel, then we can create a shallow circuit that implements U. So that's essentially the graphical proof that local invergence is a parametrization of unitary U. So now the key algorithmic idea is the following. If we wanted to train and learn an n-qubit quantum circuit U, what we do is we use this parametrization and train and learn the local inversions instead of U. So note that in the initial case, when we use the standard parametrization, let's say there's some cost function over the n qubits that we wanted to optimize over. Each of these gates might be involved in several kind of costs, like local costs, like local constraints, which kind of causes, which is like the main cost for the frustration and the main cost for having exponentially many local minimum done in previous work. But here, after we use this other representation based on local inversions, they essentially kind of decouple things. So now all we need to do is to train and learn each individual local inversion separately, and then utilize the suing technique to sue them together. So now from this algorithmic idea,
Robert, could you explain what the difference is between the local inversions and say like the standard Gibbons rotation-based approach used to synthesize a generic unitary? It sounds conceptually quite similar, but I think I'm missing something.
Yeah, so I'm not super familiar with Gibbons rotation, but somehow I thought that only works for free fermions. But here, this is an arbitrary n-qubit circuit U.
Reducing building a unitary into 2-level rotations that partially invert different subunits. And then you glue their inverses together to build the unitary. That's a standard like Nielsen and Huang way.
I see.
Prove universality. I was wondering, like, is this kind of like a block notion of the same thing?
Yeah, so this local inversion can in general be quite big, and their action might not be very like infinitesimal. They can just be a very big block of unitary that just, upon that action, it just invert that. So I would say in a way, there could be relation to that method, but I'm not familiar. So, okay. So now utilizing this learning algorithm, or utilizing this algorithmic idea, we can essentially what we showed is like training these or learning these local inversions leads to a very nice landscape, and hence one can learn shallow quantum circuits efficiently. And that results in the following theorem, which states that any n-qubit shallow quantum circuits can be learned to a small diamond distance epsilon in polynomial n and 1/epsilon time. And in practice, I mean, in a lot of situations, like a geometrically local quantum circuit, this polynomial is very small. It's like n squared over epsilon squared. However, also note that this theorem doesn't really need to impose geometric locality. The shallow quantum circuit can just have all-to-all connectivity and can be arbitrary in that case. And in those cases, it would still be polynomial, but the polynomial factor will be a bit bigger. So now utilizing this theorem, we can revisit the use cases that we have looked at before and show how it can become rigorous. So let's look at the use case 1 for learning dynamics, where just to recap, we have a training set consisting of input and output states, and the goal is to train the quantum neural network to perform simulation of this unknown dynamics. What we can show using theorem 1 is that as long as the unknown dynamics can be represented by some arbitrary shallow quantum circuit that is unknown to us, we can show that the quantum neural network training on a very simple data set, that is, the data set just consists of a bunch of random product state, as well as the output statistics, that is a random product state feed into the unknown dynamics and perform randomized measurement, randomized Pauli measurement on all the qubits. With that classical training set, one can train this quantum neural network to predict the output accurately for all input states. And the reason that it can predict all input states is because the theorem holds in the diamond distance, which is the worst case metric. So we can train on product state, and now during prediction, we can feed the quantum neural network with some highly exotic, highly entangled input states, and it's guaranteed that the output is going to be close. So in the second use case we've discussed is in speeding up dynamics. That is, we have some circuit, maybe a trautherization circuit for implementing some Hamiltonian dynamics, but we are hoping that maybe the Hamiltonian has some property such that there exists an even faster circuit implementation. So in this use case, for this use case, using the same theorem, we can show that whenever there exists some low-depth circuit implementation, the quantum neural network would be able to find that low-depth circuit implementation and allow us to speed up the simulation. So note that in order to achieve this, we need to use this parallels method that I briefly described. Essentially, that's a detail in our paper. And in particular, if there exists like a depth D circuit for implementing the unitary U, we can show that the quantum neural network will be able to find a circuit implementation of a small constant times depth D. So now for the third use case in generative modeling, recall that here there's a classical data set consisting of input tags and some output bit strings, and we wanted to train the quantum neural network to essentially generate new bit strings. We can show that by combining the quantum advantage statements that I described in the beginning of the talk with the learnability result, we easily get the statement that quantum neural networks, shallow quantum neural networks, can learn to generate classical probability distribution that are classically hard to sample from and hence have a superpolynomial quantum advantage. And here the quantum advantage is a computational advantage. So now to conclude, in this work, we showed that shallow quantum circuits, while they're known to be classically hard to simulate, all of them, the entire family, are efficient to learn using a carefully designed quantum learning algorithm. So even though there have been a lot of challenges that people face in the standard parameterization, by using this different parameterization, one can show that the landscape becomes much better and the learning can be done efficiently. Despite our progress, there are still a lot of interesting questions. For example, even though shallow quantum circuit already exhibits quantum advantage, they're still restricted in various regards. So one could ask, what about learning some deep quantum circuits? Can we also design efficient algorithm to learn? So we'd like to add on to that. We put out a paper last month. It shows a kind of a negative result. So basically in that paper, we proved that even for a relatively shallow quantum circuit, it can already become computationally indistinguishable from exponentially complex hard random unitary for any quantum algorithm. So for any quantum ML algorithm, which means that those, even for relatively shallow quantum circuits, like polylog depth quantum circuits in one-dimensional systems, they can already be, they're already hard to learn in the worst case. However, that's only holds in the worst case, and we kind of utilize these cryptographic ideas in order to cook up that very hard to learn situation. However, I do believe that there's still going to be a large family of deep quantum circuit with some structure in them that can be efficiently learned. However, characterizing what that family looks like and designing efficient algorithm for doing them is still a big open question. And that's it for my talk. Thank you so much for listening.
Okay, thank you. We have time for some questions. There's a question in the back. Do we have the microphone? In the back row?
Thank you, Robert, for the great talk. So I have a question about, do you have heuristic argument or reasoning why the special parameterization using the local inversion can help you to efficiently learn than the standard algorithm?
Yeah, so let me provide a few more insights into that. So one can imagine the following. So it's basically what happens in the previous argument for this exponentially many local minimum kind of argument is that each of these gates, they will be involved in multiple constraints, and hence and furthermore these constraints are all overlapping, which is like a standard situation that appears in like spin glass or like stat solver, and hence it naturally gives rise to some very bad landscape that are very frustrated. On the other hand, what happens in the local inversion case is that one way to think about it is like it's kind of like an over-parameterization. So each of these gates, if it's involved in different constraint, it's now kind of each of these gates would appear in multiple of these blocks. So if we go back to like the definition of local inversions, note that like in V3, in V4 there's this gate that also appear in V3, and also appear in V2, and also appear in V1, and as well as V5 and V6. And now that gate is now being over-parameterized, and is now being used in all of them. So one way to think about this is like it's a way to over-parameterize things so that things don't become frustrated. In like classical neural network literature, it's often the case that when you over-parameterize enough, then suddenly the landscape becomes very nice, and one can converge very efficiently. So I would say in a way, this local inversion contains that spirit. So that's at least one intuitive way for that I understood why the landscape become much better.
There's a question here in the front. Oh, okay. Let's go there first, and then next down here.
Thank you. As you mentioned, you highlight that shallow quantum circuits are efficient to learn and as well as hard to simulate classically. Does it mean we can think about quantum advantage experiment, which is efficiently verifiable or efficiently certified, even if when combined to random circuit sampling?
Yeah, that's a good question. I think in a way, yes, but there's different notion. Like I think in the efficiently verifiable notion, like the strongest notion is that one assumes only seeing everything kind of classically and cannot really touch the quantum thing. But here, in order to learn it, we have to like throw in different input states and then perform measurement. So in that sense, if we kind of consider efficiently verifiable in that sense, that is, we assume there's some circuit that we're trying to run, and we hope that we designed that circuit so that it will be classically hard to simulate. And now we can efficiently learn that circuit to see if we're actually running the right thing. So in that sense, it's efficiently verifiable quantum advantage. But I don't think it's in the strongest way that some theoretical computer scientists want, which is you don't get access to throwing input states into a dynamics and performing measurement. All you get are the classical bit strings that come out of it. So I would say it's efficiently verifiable in a sense, but not in the most rigorous way that people want.
Okay, please.
Thank you very much for a nice talk. Quick question. Is there an easy or simple generalization of the algorithm if I want to learn some dynamics which approximately described by shallow circuits, such as short-time Hamiltonian dynamics with local Hamiltonian?
Yeah, actually, like in the paper, because that is indeed one of the main use case that we were thinking of. Like if we go to this use case 1, most dynamics, they're not exactly by shallow circuit, but they're up to some error. So in our paper, we also had result that shows that even if the quantum circuit is not exactly shallow circuit, but up to a small error, then we can show that the quantum neural network will be able to learn up to that small error. So indeed, that can be, there's like a robustness notion that can be easily done.
Okay, I think we need to move on, but let's thank Robert again.